what you want. How does a baby get from 10 pounds to 100 pounds? Overwhelming output of anabolic hormone called growth hormone. How do you get from 100 pounds to 200 pounds? Well, a lot of ways, but testosterone happens after you got so from 10 to 100 pounds, growth hormone. 100 pounds to 200, testosterone. How do you get from 200 to what I weigh? Eat too much. No, that's another story. Anyway, but the point is, catabolic is old stuff, anabolic is new stuff. You've got to get this. So the question is, how can we optimize dietary energy management systems? How can we optimize exercise energy management systems? And why would we care? Because that's how you heal all, scratch all, just about all mitochondrial diseases. Why do you care about mitochondrial diseases? Because that's aging, degenerative disease, diabetes, Alzheimer's, coronary artery disease, osteoporosis. These are all diseases of the mitochondria. And this person has dynamic mitochondria. Let me tell you a little bit about mitochondria. A mitochondria, I wonder what I did with the lid. A mitochondria, our body, we breathe in oxygen and we burn carbon. Carbohydrates are carbons, fats are carbons, even proteins have carbons in them. Mixing oxygen and carbon is where all of the energy in our systems come from. That's where all of the energy in a car comes from. When you have a carburetor that works well, mixes well, you've got a car that runs efficiently, is powerful, and gets good mileage. When the carburetor isn't mixed well, you burn, foul the plugs, burn out the rings. We're exactly like that. It's not even interesting the difference. We're just like a car in the mitochondria. Okay, we burn carbons, we mix them with oxygen, and we have an exhaust pipe. Well, we got a couple of them. That's another. Okay, now think about that. This person has a lot of anabolic activity. They make more new stuff than tear down old stuff. And they have a very sensitive energy management system responding to diet. Okay. Corollary concept. Measure and monitor everything. If you want to make progress on that ANACAT map, you got to measure where you are, because you can screw it up. I promise you, you'll screw it up. By the way, let me define that other axis. Nope, that wasn't it. There it is. I know there are real pros at this, but we haven't done one of these in a long time. And we call it ANACAT, anabolic, catabolic map. So that axis is a surrogate's insulin. The other axis is this, HDL, not HDL, to B plus IGF-1, that's growth hormone produced by the liver, insulin growth factor type 1, plus, and this is both for men and women, free testosterone, plus VO2 max, divided by the integral of 90 days, by the way, of cortisol. Now this is a very good formula, approximation for a surrogate that defines where you are on the catabolic-anabolic axis. Fasting insulin is a pretty good, simple surrogate marker for where you are on the dietary energy management axis. Okay? Now, if your insulin's high, your testosterone's low, and you can't run upstairs without getting short of breath, this is you. If you don't have diabetes, this is still you, because you're going to have it, or you have all the diseases that go with it, even if you don't have it. If you're 98 years old, still going strong, but haven't enjoyed your life very much, there are people like this. I don't want to be too cavalier about this person I'm describing. You're in this category. These people do live a long time. If you're in this category, strong, vigorous, well, guess what? I've got the genetics, I've got the cancer, Got my dad. I'm just more vigilant. It ain't going to get me. That's the plan, okay? But there's a genetic, and who else is in this category? Many women with breast cancer are in this category. Many people with colon cancer are in this category. And why? How in the world has that got to do with mitochondrial disease? How in the world is that related? It's related this way. If your energy management systems are resistant, let's just look at insulin. By the way, this works with all the rest of them. Your insulin levels are high. You got lots of hormones, big-breasted woman, lots of estrogen, and too much insulin. Guess what? Those are markers on the surface of the cell. The cell wall, here's the nucleus, with all that DNA coiled up. That's why they call it DNA gyrase. It goes in there, unwraps that so the body can read it. And there's an estrogen receptor on there, and there's an insulin receptor on there, and there's a insulin growth factor type 1 receptor on there. And these signals have to be in balance to tell this nucleus how to reproduce properly. If these signals are out of balance, which one was which? Was this insulin? No, that's estrogen. Anyway, so this is insulin. This is that. This is growth hormone. Interesting enough, when insulin is high, growth hormone tends to be low. This signal is screwed up. It screws up the replication of the DNA. This is a well-described biological process, by the way. Now, there are other examples, but I'm using breast cancer for the moment. So if that's one of the reasons, this person, as a woman, by the way, this is Whistler's father, too. That's one of the reasons, typically, unless there have been some other hormonal interventions, a smaller breasted woman does, in fact, have a lower risk for breast cancer. It's not just that she has less volume to work with. There's some other things going on. And if you have lots of estrogen, in my example, and you're insulin sensitive, you're not going to get breast cancer either. Now, remember, got osteoporosis, tired, big gut, you're insulin resistant, you don't have much testosterone, that's you. The point about the thin skin, the dry mucosa, is that they don't have a lot of juice, okay? They don't have a lot of estrogen or testosterone or whatever, growth hormone. They don't have a lot of that, which turns out to have another corollary I left off of there, and that's this.